Okay, sure. Right, so I'm Elena Fuchs, and as you can see, my title is Local to Global Phenomena in Deficient Groups. So I'm sure some of you or most of you have heard at least of the term local to global. And if you haven't, that's fine. I'll say what I mean by that later. But maybe deficient groups isn't such a common term. So let me say what I mean by that. Actually, let me say what I don't mean by that. So if you think of SL2Z, or maybe congruent subgroups thereof, these are not deficient. So these are lattices in SL2R, and I don't think of them as deficient. Okay, so somehow deficient groups are groups that are not lattices. And maybe the best way I can tell you how these come up and exactly what they are is through an example. So this example is something I've been working on for the last few years. And it starts with Apollonian circle packings. So what are these? Okay, well, if you want to draw one, you can start with 3 mutually tangent circles, 1 on the outside and 3 on the inside. Right. Okay. All right, that's fine. Okay, so 3 mutually tangent circles, 3 inside of 1 on the outside. And the way we're going to pack circles in here is we're going to inscribe little circles inside these curvilinear triangles. And we can do this indefinitely. So we keep getting these little triangles, and we keep doing that. And what we get is a packing of infinitely many circles called an Apollonian circle packing. So why is it called an Apollonian circle packing? Well, that's because there's a theorem of Apollonius from 200 BC, about, it's pretty old, which says that to any 3 mutually tangent circles, there are precisely 2 others that are tangent to all 3. So for example, to these 3, we have the one on the outside, and so there must be exactly one on the inside here. So this means that inscribing these circles there's somehow a unique way of doing this. So otherwise, these packings wouldn't be well defined. Okay, so to any 3 mutually tangent circles, there exists exactly 2 others tangent to them. All right, so that's a while ago. More recent, Friedrich Soddy in 1937 was playing around with these. He was actually a Nobel Prize laureate in chemistry. He invented the term isotope. But he was playing around with these, and he observed that if any 4 mutually tangent circles in the packing have integer curvature, so if any 4 mutually tangent circles have integer curvature, and by curvature I just mean reciprocal of the radius, this is 1 over r, then in fact all of the circles in the packing will have integer curvature as well. So for example here, let's say the circle on the outside has curvature 1. Actually, we'll always say the curvature on the outside has negative curvature. So we'll say it has -1 curvature. And these 2, say, have curvature 2. And this one has curvature 3. Then what we know is that all these little circles we drew have integer curvature as well. So if any 4 mutually tangent circles have integer curvature, then all the circles in the packing have integer curvature. All right, so that's pretty fascinating. But where do these deficient groups come in? So there's a theorem of Descartes, 1643, which says that if you have 4 circles that are mutually tangent, so if A1, A2, A3, and A4 are the curvatures of 4 mutually tangent circles, then they satisfy a certain equation. Then Q of A1, A2, A3, A4, which is 2 times the sum of their squares minus the square of the sum, should be equal to 0. Okay, and this is, remember, taking the outside circle having negative curvature. Otherwise, this won't work out. Okay, and so this is helpful. So it's obviously a very nice formula. And remember, Apollonius' theorem says that if we have 3 mutually tangent circles, so for example, if we know the curvatures A2, A3, and A4, 3 mutually tangent circles, then there are precisely 2 others tangent to these 3. So there's A1 and so A1 prime and A1, let's say, that should be tangent to these 3 circles. And what this allows us to do is it allows us to solve, if we know these, to solve for these 2 here. So what does it give us? It actually gives us a relationship between these 2. It tells us that A1 prime is equal to minus A1 plus 2A2 plus 2A3 plus 2A4. Okay, in other words, if I have a quadruple of mutually tangent circles, A1, A2, A3, and A4, then I can use this matrix transformation, minus 1, 2, 2, 2, 1, 1, 1, to get a new quadruple of mutually tangent circles, A1 prime, A2, A3, and A4. Okay, now what is this transformation? Geometrically, it has a geometric interpretation. So if this is the circle of curvature A1, this is A2, A3, and A4. What this transformation is doing is it's taking the circle A1 and reflecting it in the circle which goes through these tangency points here. So we reflect the circle A1 in here. These tangencies are preserved with these 3 circles, and what we get is precisely the circle on the inside of curvature A1 prime. Okay, and there's actually 3 other reflections that you can do in this way. Reflections through, well, the way I drew this is actually a straight line. Through these 3 tangency points, these 3, so here's a big circle here and a circle there, like that. So there's 3 dotted circles through which we can reflect circles here, and if we keep reflecting, we'll get all the circles in the packing. So if you think about it, reflecting a circles inside of these dotted dual circles is actually equivalent to inscribing circles in the curvilinear triangles. Okay, so these 4 reflections generate some group. So the group generated by these reflections is, we'll call it A. It's called the Apollonian group for obvious reasons. Right, so what can we say about this group? Well, first of all, as we saw, orbits of this group A are somehow correspond to Apollonian circle packings. Right? If we just take any quadruple of mutually tangent circles and we look at the orbit of A acting on that quadruple, we'll get the full packing of the circles which contain that quadruple. So the orbits of A correspond to Apollonian circle packing. And there are some things we might notice about this group. First of all, A is a subgroup of the orthogonal group which fixes Q, Q being that quaternary quadratic form up there. Also, A is of infinite index in here. And actually, for this reason, you can see that there's infinitely many integer Apollonian circle packings. Also, so this quadratic form Q has signature 3, 1. So you can think of A as a subgroup of OR 3, 1. which is a group of isometries of the of hyperbolic 3 space. So A is actually, so you can think of A as acting on hyperbolic 3 space, and actually in this picture, if you think of the upper half space model of hyperbolic 3 space, the fundamental domain would be simply put 3 hemispheres here, and think of basically everything coming out, everything outside those hemispheres as the fundamental domain. So this fundamental domain of A acting on hyperbolic 3 space has infinite volume. Right, so this group A is a deficient group. In the sense that it's not a lattice. And because of that, if we want to do some sort of number theory with this, we can't use classical methods that apply to lattices. But I won't say too much about that. What I will say is you might expect naively, just without thinking about it, that because A is a deficient group like this, say the integers that come up as curvatures in a given Apollonian circle packing isn't a very rich set of integers, because A is somehow not a very rich group. But that's not true. So there's a theorem joint with Bergan, which says precisely that the integers which come up in any given integer Apollonian circle packing make up a positive fraction of all the integers. So if you count, well, kappa px is the number of integers less than or equal to x in a packing P. So by integers in a packing P, I mean the curvatures, the integers that come up as curvatures in that packing. And we're just counting them each integer once. So in that picture, we would only count 2 once. Then there exists some constant depending on the packing, which is greater than 0, such that kappa px is greater than or equal to the constant times x. Okay, so this is saying.
So kappa is just the stupid density or the fancy density?
Kappa is it's just simply the number of integers that comes up. Okay, all right. So yeah, it's just the number of integers if you start counting that come up. If you write down all the integers, that's the next.
Does every integer actually appear in some packing?
Yes. You can think of this. I mean, yeah, it does. Especially if you don't talk about primitive packings. If you're allowed to sort of multiply all the curvatures in the packing by some number, then this is trivial. Okay, so right, that's a theorem. But an even richer thing would be if we could prove a conjecture, which is precisely a local to global conjecture. And so before I write this down, let me say that we can show that there are obstructions in any, if you look at the integers that come up as curvatures in any packing, there are obstructions mod 24. Meaning that if I reduce all the curvatures mod 24, I won't get all the possible residues mod 24. But if I take some number that's relatively prime to 24, I'll get every single residue possible. But mod 24, this isn't the case. And 24 is sort of the magic number here. OK, so this conjecture is discussed at length in a paper with Sandin. And so what does it say? It says that, so if SP, I'll call it, is a set of residues mod 24 in a packing P. So take a packing, reduce all the curvatures mod 24, and see what integers you get. That's SP. So the conjecture says that there exists some big integer, x, depending on P, such that any A greater than or equal to xp, which is in this set SP mod 24, is a curvature in P. So basically here, for example, in that packing, we know 2 mod 24 is a possible residue class. So this would say that somehow if we take a big enough integer and that's 2 mod 24, then without thinking I can say, yes, it's in that packing, as it's a curvature in that packing. Right, so this is the local to global conjecture. And it's pretty difficult to prove. So if this is an open problem, if you will, to prove it. And it is supported by numerical data, at least as much as numerical data as we can get. It's supported, it seems that eventually you get all the integers you would expect. But just to show how difficult this problem is, to give you a flavor, so this is a local to global property for the group A, the Apollonian group. So instead of A, if we think about the full orthogonal group, what happens? So the full orthogonal group fixing that quadratic form, well, what we're talking about is we're thinking, can I find x2, x3, x4 which solve this equation? Can I find, so I'm given some A, some big A, and I want to find x2, x3, x4 which satisfy this equation. This is not a difficult problem. In fact, any A occurs. But you can see this is a question about somehow local to global for ternary quadratic forms. And that's Hilbert's 11th problem. That's a very difficult problem. It has been resolved, although not in quite such naive terms as written up here. And also, I would even say it's a little more difficult than Hilbert's 11th problem because we're not talking about some ternary form. We're talking about some thin subset, in some sense, of this ternary form case. So, right. And basically, what I would like to be able to do is to say, first of all, for what deficient groups one could expect such a local to global principle. And of course, it would be very nice if you could prove such a principle in any of these groups. So that's all.
Can you say why 24 is the magic number here?
Well, you can figure out that sort of the primes 2 and 3 are problematic. And then you need to sort of figure out how high a power. So basically, once for 2 and 3, for 2, for example, once you know what something is mod 8, what an orbit is mod 8, you can lift it easily to an orbit mod 16 and so on and so forth. And for 3, you can lift it to an orbit mod 9, 27, and so on. Y2 and 3, though, that's a little bit more complicated. It turns out that you can prove some sort of strong approximation-like principle for other primes besides 2 and 3.
So presumably your theorem applies to more than just the specific group A.
Yes.
I mean, how much about A do you use? Like, is it risky dense? Or
Yes, we use it as Zariski dense. And I'd say the main thing behind this theorem is that we sort of cheat in that A is this deficient group. It's not a lattice. But sitting inside of it are some subgroups that are lattices inside of smaller groups. So this A is a deficient group in OR31, but it has lattices inside of OR21s in there. And we use that very heavily for this. So I think that's sort of the key.
And without this constant CP, can you produce, it's a conjectural, this
Yes.
intermediate conjecture, which is the right constant.
Yeah, so if we could prove this, then for example, for that packing, since I think there's six possible residues mod 24, it should be 1/4. But we haven't actually computed this. I mean, we basically show that this constant should exist.
So this intermediate conjecture doesn't seem any easier necessarily.
Not so much. No, I don't think so.
If you count with multiplicity, do you have asymptotic?
Yes, I don't have an asymptotic, but if you count with multiplicity, so let's call that NP of x, there's work of Kontorovich and O. And they show that this is asymptotic to some constant, depending on the packing, times x to a power 1.3, which is the Hausdorff dimension of the limit set of the packing. Also doesn't depend on which packing.
CP is quite subtle in there. It depends on the base eigenfunction of the map. It's a serious thing. If you find another proof of that, it'll be interesting.
Is the Hausdorff dimension of the packing the same as the Hausdorff dimension of the limit set of the group? Or
Yes.
are there two different objects, really?
It's a theorem of solid.
Yeah.